All right, ladies and gentlemen, today we have lesson 7.4, part A. Lesson 7.4 has 3 different parts all built in. Instead of doing one long, complex lesson, we're going to go ahead and break it up. 7.4, part A is talking about rational versus irrational numbers. So our rational numbers, these are the numbers that you've actually been experiencing already in 6th, 7th, and 8th grade. Irrational, not so much. Our objectives today: identify and compare rational and irrational numbers, simplify irrational numbers to obtain exact and approximate answers. And some of that may be like, what? But don't worry, we will be able to help you out. Remember, the video is online, the notes are also online, so in case you fall behind a little bit, feel free to go ahead and identify which words you have missed according to that. But again, the objective should be pretty helpful. All right, we've got a few items here to be able to set up together to be able to understand what they are and then compare, contrast using some examples. Looking at our rational numbers. Numbers written as a ratio of 2 integers. My favorite way is saying fractions. So right here, a ratio, that's a fancy way of saying a fraction. So like 2 over 3, -4 over 5, and so on. Written as a ratio of 2 integers, fractions. It also does include terminating decimals. A terminating decimal is like 2.5 or 3.1. And then it also includes repeating decimals like 3.1212, which gives you a little bar at the top right. So again, the repeating part of a decimal is a rational number. And of course, our integers, the integers, again, are those numbers on the number line, like -3, -2, -1, 0, 1, 2, 3, and so on. Those are the numbers that you spent a lot of time with in 7th grade, decimals, fractions, and integers. In 8th grade, we spent a little bit more time with our fractions and integers, not so much with our decimals, but occasionally we do use them off and on. Again, 0.5 is an example of a terminating decimal. And again, that's also a fraction of 1/2. 1/2 is a rational number. That is a ratio of 2 integers, 1 and 2, so 1 over 2. That little bar, again, represents a repeating decimal. 0.3 with the bar at the top really means 0.33333. Again, a lot of threes on your calculator when you show your division. That fraction is 1/3. So again, if on your calculator you would type in 1 divided by 3, you would end up on your screen 0 point, and then again a bunch of threes, which tells us it's a repeating decimal. -9 and 7/10, of course, that can be changed into an improper fraction. A mixed number, again, maybe not the greatest form of a rational number, but you could change it again to -97 over 10, which is a fraction, improper fraction, which is really a ratio of 2 integers. The square root of 9. Now, we already know, you should have this memorized, the square root of 9. We know the square root of 9 is a simple 3. For this one, some students get, I'm not too sure. But again, if you simplify it a little bit, the 1 can stay a 1. And then our denominator, we should know the cube root of 8. The cube root of 8 is a simple 2. So that means I do have a ratio of 1/2. In fact, when you have your quiz next week, you're going to have to figure out, looking at some numbers, if they are a rational number or an irrational number. And a lot of students actually get it correct, but there's a few that make a few mistakes. And again, like that, that's one of the reasons why they say, I don't know the cube root of 8, but you really do. All right, now that we move on to irrational numbers. Irrational numbers are non-repeating, non-terminating numbers. So in other words, if you have a decimal, you may not be able to find the pattern. So there's no repeating part. So for example, maybe like 2.13, 14, 12, 03. You just got all these random numbers there. Or you might not know what that square root is, meaning you can't actually write it as a fraction, which again is a ratio of two integers. Pi is the most famous irrational number. Again, pi is 3.14, or is it? It's not really 3.14, 3.14159, and then all of these extra digits there. There's no way for you to actually write it as a fraction. Now, in 7th grade, we did tell you that approximately 22 over 7 is a pretty close fraction to pi. But again, it's not exact. So pi is an irrational number. As you see there, you got all these extra digits there. The dot, dot, dot means that it just keeps continuing on. You really don't know exactly what's coming up next. Now, we knew the square root of 9, but do we know the square root of 5? No, we don't. And if we type it into our calculator, it's actually going to give us an approximation, not an exact number. The cube root of 16. Well, we know the square root of 16, but we don't know the cube root of 16 either. It's going to give us a decimal that is non-repeating, non-terminating. Again, you just don't know it. But one of the difficult things students do is on the assessments, they say, oh, I don't know that, but they really should. They should have memorized it. Those extra dots there, we don't know what the pattern is going to be. For example, after the 9, I don't know if it's going to be another 1, 2, 3, 4, 5, 9, 1, 2, 3, 4, 5, 9. We don't know if there's a pattern. So those little dots there is pretty much telling you, yeah, we don't know. It's irrational. So what I'd like you to do is to take a moment. I will not pause the video. I will just be quiet momentarily. You're going to go ahead and write these down, and you're going to go ahead and simply put an R for rational or I for irrational. And you're going to have questions exactly like this on your homework and on your assessment. Put an R for rational, I for irrational. All right, I'm going to start my timer about a minute or so. Be awesome. Thirty more seconds. 10, 9, 5, 4. All right, pencils down. Let's see. Were you able to get each one? -3, is that rational or irrational? Rational. You can write it as a nice fraction, -3 over 1. So it's a fraction. It's a ratio of two integers. For letter B, you automatically see that pi symbol. You should be irrational. Sorry, nose itches. C, that is a repeating decimal. Repeating decimals are classified as rational numbers. Letter D, the cube root of 27. Now, this is one you should have memorized. The cube root of 27 is a 3, therefore it is a irrational number. Letter E, the square root of 5. That was actually from our previous slide. We don't know the square root of 5, irrational number. Now, what about this one? This is where some students choose to say, I think it's this answer, others disagree. Now, I see a 45, 45, 45. Now, some students would assume that it would continue on, therefore it is a repeating decimal. However, as I shared with you, those little dots there, there's no guarantee. We really don't know, so we're going to say irrational number there. So again, the little hint to remember is if you see those little dots, we just don't know. All right, there's the lights. Silly automatic lights. All right, we have already talked about memorizing our square roots, but there are some that we don't know what the square root is, but we can simplify. And that's usually, I don't want to say a very large number, but it's definitely a number that we could break up into different products, or sometimes called factors. And you've actually done this before in elementary school. They are called factor trees. So we're going to go ahead and take our square root of 64, which we already know is a simple 8. But we may want to go ahead and break it up using a different strategy. Now, if you didn't know the square root of 64, you could break it up into your factor tree, and you would be looking for prime numbers. But the benefit of knowing your perfect squares is that some of them, you just know what the square roots are. The square root of 64 is 8, so therefore it is a rational number. But we don't know what the square root of 54 is. I might be able to break this up, simplify it, and then determine if it's rational or irrational. As we do our work together, we're going to learn that this is actually an irrational number. Later on in our lessons, we are going to learn how to actually approximate that to a decimal value. So maybe it's like 7.5, or is it 7.8? And I don't have a calculator. What am I supposed to do? Because again, we're not going to allow you to use calculators on your assessments, for this chapter at least. So our focus today is to try and simplify this square root that is not a perfect square root. Two ways to simplify our irrational numbers are as follows: the factor tree and the number line. So we're going to focus on the factor tree today, and then we'll focus on the number line a little bit later. But to just give you a heads up, the square root of 8, we do not know what the square root of 8 is, but we can break it up into a factor tree that will give us a result of called, which we say in our upper level math, 2 radical 2. We understand that this means 2 multiplied by the square root of 2. But to try and save you guys some time, we call it 2 radical 2. One more time, we call it 2 radical 2. So in high school, you're going to be dealing with all these different radicals involved, even some advanced imaginary numbers in high school, to just try and advance your thinking. This gives us an exact answer. Even though we don't really know what it is, like if it's a decimal with a 5, a 6, or 7, or whatever, this is called an exact answer. Just like when we get to our volume problems in Chapter 8, an exact answer would contain a pi symbol. An approximate answer, though, would be a decimal number, which is going to be on the number line that we're going to learn later on and say, okay, it's in between the square root of 4 and the square root of 9. So it means it's somewhere in between a 2 and a 3. If you notice, it's a little bit closer to the square root of 9, which means it's a little closer to 3. So is that a 2.7, 2.8, 2.9? Is it a 2.92? We really don't know yet, but we're going to discover that later on. Again, that's an approximate answer. When we talk about our volume problems later on in Chapter 8, an approximate answer would be using a decimal form for pi. The exact answer would be with the pi symbol. So in other words, they're very close, but one is exact, one is approximate. When you are sending people, hopefully, to Mars in the future, you want to be using exact numbers, not approximate numbers. All right, so this is our factor tree strategy. Your goal is to break it up using your factors or your multiplication skills so that you would only have your prime numbers remaining. So let's see, 54. You could break it up into 2 numbers. Now, there's a few different ways to do that, but usually students would say 9 times 6. A select few students would say 2 times 27, but majority would say 9 times 6. Now, we know that 9 is what is called a composite number, not prime, and 6 is also a composite number, not prime, which means I'm not done with those numbers. I need to break them up further. So it means my 9 is really a 3 and a 3, because 3 times 3 is 9. And my 6 is a 2 and a 3, or a 3 and a 2. Those are the numbers that I'm going to focus on. We are not going to focus on the 9 and the 6 because those are composite. We're going to focus on 3, 3, 3, and 2. We're going to try and find out what the pairs are, and quote unquote, like it says there, the leftovers go inside. Do you guys like leftovers? I do. Leftover pizza is my favorite. So again, the pairs go on the outside of the radical, the leftovers go on the inside of the radical. Now, if you notice, looking at the 3, 3, 3, and 2, is I actually have a simple pair of 3s. So I'm looking at the numbers at the end of the tree branches like it says there. I circle my pair that I've got. The leftovers are identified as well. The pair goes outside, the leftovers go inside. So if I have a pair of 3s on the outside of the radical, I'm not going to put a 3 and a 3. I'm just going to put the pair, kind of like when you guys are playing cards, and if you have a pair of jacks, you put them together and it's one pile. So we're going to say our answer is made up of that pair of 3s, or just a single 3, and then the leftovers go inside. Well, the leftovers go inside and they remultiply. So 2 times 3 is going to be a 6. So this is our exact answer. You've got the number in the front, which essentially is the coefficient, and then we have radical 6. So our exact answer using the factor tree method is going to be 3 radical 6. And that's what we're going to ask you to do with square roots, but also cube roots. We're going to go ahead and break it up using our factors, and then look for pairs. All right, so let's try this one right here. Again, remember, there's a few different ways to break up these problems. Some students might break them up a little bit differently than others. So the one thing I notice is it ends in a 0, so we may want to say 10 multiplied by 18. That's probably the easiest way to break it up if it ends with a 0. If it ends with a double 0, then you would break it up with 100 multiplied by the other number. Those are not prime, so I continue on, and I say a 10 is really a 2 and a 5, or 5 and 2. Because remember, in elementary school, you learn that the multiplication order doesn't matter. 5 times 2 is the same thing as 2 times 5. But let's break up our 18. Again, there's a few ways to do that. Some students might say 2 and 9, others might say 3 and 6. It doesn't matter as long as you don't stop at a composite. So 2 is a prime, but 9 is not a prime. So I need to break up my 9 to be 3 times 3. All right, I'm going to look at the end of the branches. I've got a 5, a 2, a 2, a 3, and a 3. I'm going to look for my pairs, and I'm going to look for my leftovers. Now, if you notice, I've got a pair of 3s, I have a pair of 2s, and then my 5 is the leftover. So the good news is we only have one leftover on this problem. But for our pairs, I have a pair of 3s and a pair of 2s. So I need to remultiply them together to actually find my answer. So that would give me a 6 radical 5 for my exact answer. So as we continue with the square root idea of looking for pairs, when we get to our cube roots, like this one here, we're actually going to be looking for triples. Because remember, the cube root and the cube cancel each other out. So if I can find a triple of the same number, it's the same thing as a cubed number. Now, sometimes students may struggle on where can I start. I don't know my multiplication skills as well as I should. If you notice, 128 is an even number, so you could always divide even numbers by 2. If it was an odd number, maybe you can divide by a 3, maybe a 5, maybe a 7. But again, an even number, you could always start with a 2. 2 is prime, so I pause there, and I break up my 64. 64 is an 8 times 8. Those are not prime, so I continue to break those up using my factor tree. 8 is 4 and 2. Another 4 and 2. But again, if you notice, I've got some 2's, which is great, but I've got 4's. 4's are composite. I want prime, so I break up my 4's. All right, I've got a bunch of 2's. Now, in elementary school, again, you were doing your prime factorization, which means you took all your prime numbers, you counted how much you had, and then you wrote it as an exponent. That's not what we're doing here. We're looking for either pairs on a square root or triples on a cube root. Since this is a cube root problem, I need to find my triples. So let's go ahead and circle those 3. That's a nice triple. I notice I've got that. You can do like one big circling if you'd like to, or you can say, okay, those are a triple there. And that's all the triples that I have. So then I look at the remaining branches and I find my leftover, which is a simple 2. So I have one triple 2's, another triple 2. So that's the beginning part, 2 times 2. I've got my leftover, which is my radical, but since it's a cube root, I also have to keep it as a cube root there. My final answer, which is an exact answer put together, is 4 cube root of 2, which really, again, means 4 multiplied by whatever the cube root of 2 is, because we don't know what exactly that is, so that's why we leave it as a radical. Later on, again, we will learn how to do approximate answers using a number line method. All right, for this one, we're actually going to go backwards. It says express each mixed radical in entire radical form, which means, like on this one right here, this is my exact answer. So I'm actually going to travel backwards and end up here at the top. But the good news is, if you follow our strategy, it's not as dependent upon the branches. So this is what we do. We know that we have a radicals 2 still inside, so we need to put this 4 back inside. And if you remember, it was a pair that was outside for a square root. So this is our strategy. You're going to move it inside by talking about the pairs mentality. Now, even though 4 wasn't a prime, we can still use the pairs idea. So again, if you bring it inside, you need to write a pair of it. Then you just multiply it back together. 4 times 4 is 16. 16 times 2 is 32. Or 2 times 4 is 8. 8 times 4 is 32. So we're going to say it is radical 32. Or the square root of 32. Now for later on, we know that the square root of 32 is pretty close to the square root of 36. The square root of 36 is 6. So that means the square root of 32, an approximate answer might be like 5.7 or 5.8. We'll talk about that a little bit later. All right, let's try another one. Same idea. You've got 6 radical 3. Since we're talking about a square root, we have a pair in our mind. So we go ahead and move it to the inside of the radical with the pair. We go ahead and multiply our 3 numbers together. 6 times 6 is 36. And 36 times 3, well, that's a little bit bigger than 100. We've got 108. Remember, on your assessment, you're not allowed to use a calculator. And I'm double checking what I'm editing right now. Oh yeah, we got stuff right there. Very nice. All right, to end us off, we've got some cube roots. Now remember, a square root was a pair. Our cube root, we're looking for a triple. So that means inside my cube root, of course, I've got my 5. But if I'm talking about a triple, I need to write it like this. 2, 2, and 2. Again, it's a triple. We multiply them all back together, and we get the cube root of 40. Let's see, one more. Oh, that was our last one. All right, we're going to go ahead and finish off 7.4a. Again, we were learning how to simplify radicals by using our factor tree method. And then we were learning how to go backwards and trying to write a simplified radical or cube root back into its original form. And then, of course, at the very beginning, we were talking about the difference between a rational and irrational number. These pieces not only will be on your assignment, but they will be on your assessment. All right, go ahead and be awesome and do the best that you can with the remaining time in class to work on your assignment. Have a great day.